right beneath the feet of millions of people in the Pacific Northwest, a massive tectonic event is unfolding at this exact moment, and absolutely no one is feeling a single vibration. Millions of tons of deep continental crust are currently shifting in complete silence. We are actively tracking the release of kinetic energy equivalent to a magnitude 6.8 earthquake, an event that would normally buckle highways, shatter concrete foundations, and trigger widespread power grid failures. Yet, the surface of the Earth remains completely undisturbed, hiding a planetary-scale energy transfer that is actively rewriting the geological stability of the entire region. It is a deeply unsettling realization when you look at the raw, real-time telemetry and understand that the solid ground is shifting right now, driven by thermal and gravitational forces so immense that human engineering is essentially irrelevant. The general public goes about their daily routines, navigating their morning commutes and operating within a fragile infrastructure, completely oblivious to the fact that the crust they live on is being systematically loaded with unimaginable, invisible stress. To understand the sheer magnitude of what is happening in the deep crust, we have to establish the baseline mechanics of the Cascadia Subduction Zone. This is a massive convergent tectonic plate boundary stretching roughly 1,000 kilometers along the Pacific coastline, from the shores of Northern California all the way up to Vancouver Island. Here, the dense basaltic oceanic rock of the Juan de Fuca Plate is relentlessly driving itself eastward, physically plunging beneath the lighter granitic rock of the continental North American Plate. In a standard geological model, the shallow portion of this massive fault line should be completely locked by extreme friction. It is designed by physics to accumulate immense tectonic stress over centuries, storing potential energy until the rock simply cannot hold together anymore, resulting in a sudden, violent, massive rupture. But the Earth is not a simple, predictable machine. The telemetry we're receiving from deep boreholes and surface arrays paints a far more complex, highly volatile picture of what is happening miles beneath the surface. The Juan de Fuca Plate is actively moving at roughly 40 millimeters per year. Over a century, that equates to 4 solid meters of oceanic crust trying to force its massive volume directly into the Earth's mantle. The friction coefficient of the silicate rock in this subduction zone is incredibly high. If you want to understand how these planetary engines are shifting the ground beneath our feet, and if you want to track this real-time telemetry with me, make sure to subscribe to the channel so we can monitor these anomalies together. We monitor this intense geological standoff utilizing the Pacific Northwest Seismic Network, or PNSN, operating in tandem with continuous satellite telemetry. The primary tool for detecting these silent shifts is the Global Navigation Satellite System, or GNSS. This is not the standard location tracking used in consumer electronics. We are utilizing a constellation of satellites positioned in medium Earth orbit, roughly 20,000 kilometers above the surface of the planet. These satellites contain highly precise atomic clocks, transmitting dual-frequency L-band microwave signals down through the ionosphere to surface receivers. These receivers are anchored deeply into the continental bedrock, designed to measure the phase of the carrier wave as it arrives from space. By analyzing the delays in the signal caused by the total electron content of the ionosphere, geophysicists can track the physical movement of the North American Plate down to the millimeter. When we look at the time series data from these GNSS stations over the long term, we do not see a smooth, continuous eastward progression of the continent. Instead, the data reveals a jagged, incredibly unnatural sawtooth pattern. For many months at a time, the continental edge is pushed backward, compressed eastward like a massive geological spring being slowly wound tight. And then, suddenly the telemetry reverses. The satellite data shows the massive stations drifting westward by several millimeters over the course of just a few weeks. This is the exact mathematical signature of a slow slip event, a phenomenon deeply embedded within the episodic tremor and slip, or ETS, cycle. To understand why the deep crust slides silently instead of snapping violently, we must track the intense life cycle of the oceanic crust itself. When the Juan de Fuca Plate is initially formed at the mid-ocean ridge, it is scorching hot, upwelling magma that is instantly quenched by freezing seawater. As it cools, the rock fractures extensively, creating a highly porous basaltic matrix. Over millions of years, as this oceanic slab travels toward the continental coast, deep hydrothermal circulation drives freezing ocean water miles down into the crustal rock. This water does not merely sit in the cracks, it becomes chemically bound to the rock itself through complex molecular reactions. The heat and seawater interact with the basalt to form highly hydrated minerals, primarily serpentine and chlorite. The oceanic slab essentially becomes a massive creeping sponge, carrying millions of megatons of chemically bound water directly toward the subduction zone. As the plate ultimately dives beneath the North American continent, it enters a realm of exponentially increasing thermal and lithostatic extremes. As the slab reaches depths of 25 to 40 kilometers, the environment becomes incredibly hostile. The ambient temperature within the mantle wedge exceeds 400 degrees Celsius, and the sheer weight of the overlying continent pushes the physical pressure into the realm of gigapascals. Under these extreme crushing conditions, the hydrated minerals within the subducting plate become thermodynamically unstable. The rock is literally being baked and crushed simultaneously, forcing a violent metamorphic phase transition deep within the atomic lattice. The relatively low-grade greenschist facies rock transforms into a denser blueschist, and as it plunges even deeper, it eventually compresses into incredibly dense eclogite. During these molecular phase transitions, the crystalline structure of the rock is forced to reorganize into a tighter volume. Because of this intense structural collapse, the chemically bound water is violently expelled from the crystal lattice. This is the fundamental geological process known as dehydration embrittlement. However, this newly expelled water cannot simply flow upward and escape. The overlying continental mantle wedge is composed of incredibly dense, effectively impermeable rock that acts as a massive hydraulic seal. The expelled water is entirely trapped within the deep fault zone, unable to vent to the surface. Because of the immense heat and crushing pressure at these depths, this water is no longer behaving as a standard liquid or a gas. The temperature and pressure force the water past its critical point, specifically 374 degrees Celsius and 22 megapascals of pressure. Beyond this strict thermodynamic boundary, the fluid enters a supercritical state. This phase of matter is entirely alien to surface environments. Supercritical fluid possesses the high density and solvent capabilities of a liquid, but it flows with the low viscosity and rapid diffusivity of a gas. It effortlessly penetrates every microscopic pore, intergranular boundary, and microfracture within the deep rock matrix. As the metamorphic reactions relentlessly continue within the descending slab, more and more supercritical fluid is continuously pumped directly into the fault zone. Because the fluid is trapped by the impermeable mantle seal above it, the pore fluid pressure begins to rapidly skyrocket. In subduction zone geophysics, we calculate stability by analysing the effective normal stress acting upon a fault. This is defined as the lithostatic pressure, the sheer physical weight of the continent clamping the fault tightly shut, minus the internal pore fluid pressure pushing the fault apart from the inside. As the supercritical fluid pressure builds to extreme levels, it actively counteracts the massive weight of the overlying North American plate. The fluid physically separates the two tectonic plates on a microscopic scale, causing the effective friction on the fault interface to drop to near zero. The fault is, quite literally, being hydraulically unzipped from the inside out. This extreme, highly localized overpressure perfectly lubricates the deep plate interface, allowing the immense Juan de Fuca plate to slowly, silently slide forward, rather than catching and snapping violently. But this is exactly where the narrative reaches a severe threshold, because this deep, lubricating slip is not a geological relief valve. It is a profound systemic failure mechanism. The system reaches a critical point where the deep, ductile crust can no longer absorb the incoming kinetic energy. When the deep fault slowly slips over the course of several weeks, the immense plate movement does not simply dissipate into the mantle. Instead, the slow slip in the deep hot zone actively and aggressively transfers millions of tons of unyielding tectonic force directly up dip, straight into the shallow, fully locked portion of the fault. The very mechanism that temporarily prevents a deep, catastrophic earthquake is systematically guaranteeing a much larger, infinitely more destructive shallow rupture. Let us step back from the microscopic mineral transitions and look at the vast, terrifying scale of what this means for the surface of our planet. Directly above this active slow slip zone sits our most critical human infrastructure. Vast metropolitan corridors, highly complex power grids, and sprawling natural gas networks are resting entirely unaware of the immense geological loading happening just miles below their foundations. While the deep fault is actively sliding, the upper 15 to 25 kilometers of the Cascadia megathrust remains completely, unyieldingly locked. The ambient temperature in this shallow seismogenic zone is simply too low to allow for plastic deformation or slow creeping movement. The rock here is cold, incredibly brittle, and firmly stuck together by immense unlubricated frictional forces. When the deep plate slowly creeps forward over the course of 2 to 3 weeks, it physically drags the deeper, hotter roots of the North American plate eastward with it. However, the upper cold portion of the continent remains entirely snagged on the locked fault interface. This physical dynamic creates an extreme shear gradient across the continental crust. The massive stress generated by the moving plate does not simply vanish into the ether. Fundamental physics demands the strict conservation of energy. The staggering kinetic energy of the creeping Juan de Fuca plate is forcefully converted into stored elastic potential energy within the locked seismogenic zone. We are actively watching a planetary-scale spring being forcefully wound tighter and tighter, month after month. We meticulously track this up-dip stress transfer using deep borehole strainmeters. These are incredibly complex, hypersensitive scientific instruments. They consist of incredibly delicate metal cylinders packed with specialized electronics, permanently cemented into solid continental bedrock hundreds of meters below the surface. These instruments are designed to measure volumetric strain, the actual physical stretching, compressing, and warping of the Earth's solid crust, down to mere parts per billion. To put that staggering sensitivity into perspective, a deep borehole strainmeter can literally detect the microscopic gravitational pull of the moon warping the solid rock beneath it, or the physical weight of a heavy rainfall compressing the surface crust above. When an episodic tremor and slip event begins deep below, these strainmeters go absolutely wild. The continuous data stream, normally a quiet, undulating baseline of standard tidal fluctuations, suddenly spikes with undeniable, massive tectonic deformation. The solid bedrock surrounding the locked fault is being forcefully bent, forced to physically accommodate the new, distorted geometry of the slipped plate beneath it. Through these instruments, we directly observe the continental crust bending, warping, and silently storing millions of joules of highly volatile elastic energy. Think about the heavy foundations of your local bridges, the massive high-voltage transmission lines strung across the landscape, and the highly pressurized underground gas mains buried in your area. How much silent millimeter-by-millimeter crustal deformation do you think that aging, rigid infrastructure can actually withstand before the latent shear stress forces it to silently fail? Let me know in the comments how your local grid handles even minor environmental stress, because the unyielding geological forces we are actively tracking are orders of magnitude larger and far more persistent. Along with the silent deformation recorded by the strainmeters and GNSS arrays, there is a secondary, deeply unsettling acoustic signature tied to this phenomenon. The Pacific Northwest Seismic Network continuously detects thousands of tiny, highly localized, low-frequency earthquakes, classified by geophysicists as tectonic tremor. Unlike standard sudden earthquakes, which produce sharp, destructive, high-frequency compressional primary waves, this unique tectonic tremor looks entirely different on a seismogram. It registers as a low, continuous, almost rhythmic rumble. It lacks the sharp P-wave onset entirely, consisting almost exclusively of low-frequency shear S-waves oscillating between 1 and 10 Hz. In standard seismology, these low frequencies are frequently filtered out as background noise. It requires highly complex cross-correlation techniques across massive, multi-station seismic arrays to mathematically isolate and locate the deep source of these waves. This continuous rumble is the literal sound of the deep fault slowly tearing and chattering. It is the acoustic echo of the highly pressurized supercritical fluids aggressively pushing their way through the deep rock matrix, forcing the plate to grind forward inch by inch. This tectonic tremor is the acoustic heartbeat of the subduction zone, and it beats with an incredibly precise, deeply unnerving mathematical rhythm. Geophysicists have spent decades mapping this exact rhythm, and the predictability of the data is staggering. In the central portion of the Cascadia Subduction Zone, deep beneath the Puget Sound and stretching northward toward Vancouver Island, these episodic tremor and slip events occur on a relentless schedule. They trigger almost exactly every 14 months. Every single 14 months, the deep plate begins to slowly slip, the low-frequency tremor aggressively flares up across the seismogram network, and massive amounts of concentrated tectonic stress are hurled directly up-dip into the locked megathrust. It is a relentless, entirely unstoppable geological clock, and it is ticking right now. To truly grasp the existential gravity of this data, we must discuss exactly what happens to the shallow crustal rock during these highly repetitive 14-month cycles. The solid rock within the locked seismogenic zone is being actively subjected to intense cyclic loading. In advanced materials science, we know definitively that subjecting any rigid material to cyclic stress ultimately leads to profound structural fatigue. As the deep plate slips and loads the upper fault, microscopic fractures begin to propagate within the tightly bound, crystalline structure of the fault zone. The rock is experiencing a physical phenomenon known as strain hardening. The continued relentless deformation causes the mineral lattices within the fault to become increasingly brittle over time. The physical capacity of the fault rock to absorb further stress without catastrophically shattering is actively, permanently being reduced with every single slow slip cycle that passes. Furthermore, we have to calculate the strict parameters of Coulomb stress transfer. When a geological fault slips, it fundamentally alters the surrounding regional stress field. It locally decreases the stress in the specific area that just moved, but it significantly, dangerously increases the stress at the absolute edges of the newly ruptured zone. Because these slow slip events originate in the deep, hot crust and actively propagate upward toward the cold, locked zone, they are fundamentally altering the Coulomb stress on the deepest, most vulnerable edge of the locked fault. The slow slip is effectively eroding the bottom edge of the locked zone. It is slowly, systematically eating away at the only frictional barrier holding the entire North American continent in place against the descending oceanic slab. We are actively measuring the steady, highly rhythmic drumbeat of the locked zone being pushed irreversibly past its absolute frictional limits. The mathematics governing this process are cold, entirely rigid, and completely indifferent to human civilization or our fragile surface infrastructure. The Cascadia Subduction Zone has historically ruptured roughly every 300 to 500 years, producing massive magnitude 9.0 or higher megathrust events that permanently alter the continental coastline. The last major rupture, deeply verified by geological core samples, coastal subsidence records, and orphan tsunami logs from Japan, occurred in the year 1700. We are currently sitting well within the statistical window for the next massive, unavoidable tectonic realignment of the North American coast. The deep, slow slip events we track with the GNSS satellite arrays and the ultra-sensitive borehole strainmeters are not temporary anomalies. They are the exact, undeniable mechanism of our current geological trajectory. Every 14 months the stress clock advances forward. Millions of tons of unyielding kinetic force are irreversibly transferred directly into a fault system that is already bowing and warping under the immense accumulated pressure of 3 centuries of silence. The continental crust is actively warping beneath our cities. The supercritical fluids are continuously lubricating the deep shear zones, and the locked megathrust is forced to absorb the massive kinetic energy of an entire planetary plate moving against it. There is no engineered solution on Earth to stop this process. There is no human infrastructure capable of resisting or deflecting the movement of a massive tectonic plate. We are simply temporary passengers living on the thin crust of a highly volatile, thermally driven planetary engine. We can only watch the continuous telemetry flow into our networks as the crust systematically prepares for a profound, inevitable geological shift. The forces of deep dehydration embrittlement, massive pore fluid overpressure, and up-dip stress transfer are operating on a physical scale that completely dwarfs human existence, and they will continue their relentless 14-month cycles until the frictional strength of the locked zone is finally completely overcome. The massive data streams from the PNSN network are updating constantly, and this deep geological clock continues to tick whether we choose to acknowledge it or not. We will be meticulously tracking these deep crustal stress transfers and analysing the raw, real-time telemetry as this highly volatile situation actively evolves beneath our feet. If you want to stay informed on the exact physics driving our planet and receive the next deeply technical situational update on this specific seismic anomaly, subscribe to the channel and keep your eyes intensely focused on the data.